Okay, so for my video, I'm going to do the problem from the quiz today, which I believe was quiz 6. So we have a circuit that system in steady state operates at a frequency of 30 hertz. Right, so we know it's 30 hertz. That's providing a voltage at a frequency. So we automatically know it's going to be a complex power problem. Right, so we got 3 loads. Right, we have voltage coming this way, and then got load 1, 2, 3. Um, Given information we have is we know it's 150 angle degrees 0 voltage RMS, frequency of 30 hertz, and we know that these are all in parallel and they all see the same voltage. Right? The loads, I mean. So you got 2 parallel here. Load 1 and 2 see the same voltage. Um, so anyhow, first thing we want to do is start with the calculation of the complex power loads, right? So we know that load 1 absorbs 300 watts, delivers 250 bar, right? So automatically know power 1, P1 is 300, and Q1 is negative 250J, right? So that's this one now is those two combined. We got load 1 out of the way. Load 2, same thing. Need to figure out the complex part. Load 2 absorbs 375 volt amps with the leading power factor 0.35. We'll talk a little bit more about that in a bit. So power factor 0.35, cosine theta, inverse cosine of theta will give you the actual angle of the power factor 69.5. So we know this from the formula table, P2. All right, so 375, which we found up here, right? 375 volt amps. We're going to find that was actually given, sorry. So we calculate the real power, P2, absolute value of S2, cosine theta. So it's 137.25 watts. Q2 is negative 30, excuse me, the complex portion of it, right? Negative 375 sine theta, 375 times 0.937. So then we know S2 is this here. Okay, same thing for load 3, right? So we got load 1, we got load 2. I find load 3 now. So it absorbs as what we're given is 400 minus 15 degree. All right, with that, you can find P3, find Q3 as well. And we're given that here. So now we got S3. So we got S1, S2, S3, right? So now we found the complex loads for all of them. Now we basically need to combine them to find the total complex power. So we're essentially adding all the complex powers to get what the source must supply. So in this instance, what we're doing is we're defining S1, 2, 3, and break it down between P total and Q total. Right. So we've already found these 3. 1, 2, 3 from above. We've already saw complex portion of them as well. 1, 2, 3. Add them all up. So S total is the real portion and the complex portion, right? Right. So the absolute value S total. We know this from formula table as well. Square this. Oops. I did that. Square that. Square that. And find the square root. Okay. And that gives us S total. So now, again, we're trying to find the current of the system. So in order to find the current, we got to find the load. In order to find the load, we got to break it down from each little load, make one big load essentially. Okay, now we've done that. So now we've got S total. So now we want to solve the current, solve for source current in the phasor domain, which we've been in. right? So here's the formula for that. And what we basically do is we'll write out um, that Ix equals S total O ES, which is what that is. Well, again, this is off from the formula sheet as well. This is everything that we found already. So we got S total, VS was given. So now to find Ix, we just divide S total by VS, the absolute value, that is, of course. That gives us the amperage. So the current X RMS is now this. Okay. Now find, go back into the time domain. We convert from RMS to peak. In order to find that, you do square root 2 times this amperage there, right? So and then we found um, 188.5 back up here, right? So that's it. We found the current using the peak. So we're now in the time domain. Cosine 188.5t plus 31.3 amps. What's your answer?